Okay, this one says find the volume of the solid bounded between the paraboloid blah 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 z equals 1 minus x squared minus y squared and the plane z equals 1 minus y. So let me show you what this would look like. 1 minus x squared, 1 minus x squared minus y squared. That paraboloid looks like that. Okay. The plane 1 minus y looks like that, right? And so the question is asking, find the volume of the solid bounded between these two. So between the paraboloid and that plane, there's just a little bit of volume sandwiched in between those that kind of looks like an ellipse, but it's a little bit lopsided, like it's a little bit fatter on one side of the ellipse than the other. You see what the region I'm talking about in between? Okay, so that's what we're trying to find, is that volume. And so if the blue axis is my z-axis, then it looks like the paraboloid is on top of the plane. If you couldn't graph this, I'll try to explain how you would know that anyways, if you can't graph it, right? So the first thing I'm going to find with these types of questions, if I'm talking about two surfaces and the volume between them, is number one, find the intersection of the two surfaces. And so the intersection is going to be the places where these surfaces have the same z value. And so that would be the place where 1 minus y is equal to 1 minus x squared minus y squared. Basically, what values of x and y make that equation true? Those would be the values of x and y that give me the intersection between these two surfaces. So let me rearrange this and write something like y squared plus x squared minus y equals 0. So, we're going to do something called, well, let me see if I have to do this actually. Yeah, I think I do. Okay, so we're going to do something called completing the square. So I hope you remember this from algebra. Actually, we did this in calculus too for a few problems. But completing the square means whenever I look at just the y portion of this, y squared minus y, there's a constant that I could add to y squared minus y that would make everything in the parentheses what we'd call a perfect square quadratic polynomial. And again, this is just really an intense algebra topic, but the answer in this case is going to be 1/4. Yeah, thank you. Okay, because the definition of a perfect square is one where you can write the whole polynomial as x minus r squared. But that would mean that your polynomial looks like x squared minus 2rx, supposed to be an r, plus r squared. And if you've got something like x squared plus bx plus c, that would mean the relationship between b and c is that b over 2 squared should give you your constant. So you look at the number, you look at the coefficient of your x term, and then you divide it by 2 and you square it, and that's the constant that we want to add to this to make it a perfect square. And so in this case, the coefficient in front of my y term was -1. So I did -1 divided by 2, -1/2, then square it, and you get +1/4. That's the constant that I want to add. But if I add that to the left side, of course I have to add the same thing to the right side to keep my equation balanced. And now, the reason I did that is because I can rewrite that perfect square as y minus 1/2 squared. Okay, so now this is actually the equation for a circle with radius 1/2 and center at the point 0, 1/2. Okay, so lots of stuff to remember back from algebra from that problem here. But the green axis seems like it's my y-axis, and so you can tell when y is equal to 1/2 and x is equal to 0, that's the center of this circle, and the radius goes up to 1/2 in all directions. So that intersection between that plane and that paraboloid is a circle. Cool. So, one way you could figure out which is on top, if you weren't able to graph this, you might ask, is the paraboloid on top or is the plane on top? Kind of important to know. And so what you could do is you could plug in the coordinates of the center of your circle into both the plane equation and the paraboloid equation, and you can see which z value is greater. And so the center of my circle, right, has the coordinates x equals 0, y equals 1/2. For my plane, z equals 1 minus y, and for my paraboloid, z equals 1 minus x squared minus y squared. So for the plane, z is equal to 1/2, and for the paraboloid, z is equal to 1 minus 0 squared minus 1/4, so z is equal to 3/4. And since the paraboloid has the greater z value, that's how I could tell that the paraboloid is going to be on top of the plane, even if I don't have a graphing utility, right? Even if I were taking an exam with pencil and paper and I didn't have a good graph of this thing. So paraboloid is on top, and now I can restate this problem as find the volume of a solid. Find the volume of a solid over R with basically this formula for my integrand, and it's going to be 1 minus x squared minus y squared minus 1 plus y. Or I should say minus 1 minus y. So this, of course, is my paraboloid equation. And since I know it's on top, I'm doing top surface minus bottom surface. So paraboloid minus the plane. And then whenever I say R, of course, the R region that I'm talking about is the region where these two surfaces are intersected. And so my R region is going to be the circle where the center is at y equals 1/2, x is equal to 0, and it has radius 1/2. This is my R region. So the boundaries of that region are the intersections between the surfaces. And that's going to be a double integral. And you've got to decide on some kind of order of integration. Let's just say dx dy for right now, and if it doesn't work, then we can try something else. But my y variable can be anywhere between 0 and 1. The bounds are always going to be constants on my outside integral. But then for my inside integral, I can't just allow x to be between negative half and positive half, because that would give me the whole rectangle, give me the whole square. But instead, I have to make x a function of y, and so this is going to be minus the square root of
1/2 square minus y minus 1.
Yeah, 1/2 squared minus y squared up to positive square root of 1/2 squared minus y squared.
Minus y minus 1/2 squared.
Oh, thank you. Thank you. Yeah. Sorry, the circle is centered at 0/2, and so I can't just subtract y. I have to subtract y minus 1/2, all squared. Okay. The same for my lower bound. That's a good catch. This was kind of a hard problem. Okay, and then again my integrand is going to be 1 minus 1, that cancels out, and then I'll have negative x squared minus y squared plus y. My region that we were talking about, between 0 and 1, because the center of my circle is 1/2 for my y value. So it's this circle in the plane, right? And so we just did the order of integration where it was dx dy. So now if we wanted to do a double integral dy dx, then I would say my outside integral should have constants as the lower bound and upper bound. So I'm going to say my x variable is allowed to be anywhere between negative half and positive half. Then my y variable on the inside would be allowed to be anywhere between the bottom semicircle and the top semicircle. So to get the bottom semicircle, this would be the 1/2 minus the square root of 1/4 minus x squared. And then the top would be 1/2 plus the square root of 1/4 minus x squared. So if x is equal to 0, just think to make sure it works for some points. If x is equal to 0, 1/4 minus 0 is 1/4. The square root of 1/4 is 1/2. And so I have 1/2 minus 1/2 for my lower bound, which is 0. And for the upper bound, if x is equal to 0, that's 1/2 plus 1/2. So then y is 1 at the point x equals 0. And then you can try figure out what happens if you plug in x equals positive or negative half. Squaring it would give you 1/4, and so we have 1/4 minus 1/4, which is 0. Square root of 0 is 0. And then your y value should only be 1/2 when x is equal to positive or negative half. And so you can just double check to make sure your bounds on your y variable make sense in that case.